Hello, everyone. We're going to talk about computing with Boolean values now. And this is a small part. It's like an in-between part of the two sections for this unit, 2-2. But it's an important one because it's important that we know exactly how Boolean operators work, more so than just x is greater than 5. There's a lot more involved there, so we want to take a look at the details. So let's go ahead and get started. So in this section, this is all part of chapter 8 of your Zell book. We're going to talk about the basic idea of Boolean algebra. So equations, we're used to algebraic equations or formulas, but these are equations that are just true, false Boolean equations, and being able to analyze and write them so we can work with those Boolean operators. And we have if statements and we have while loops, and those are great. We're going to talk about while loops in that loop structures lecture. But they all use Boolean expressions, which all evaluate out to true and false. And we can compare two things, like if x is greater than or equal to 0, and that's fine. But we need to be able to do more with Booleans because you're going to end up trying to deal with multiple values that may be true or false, and you're going to have to make decisions based on them, especially when you write things like an interactive video game, which is something you're going to be doing this semester. So in an interactive video game, so many things could be happening at any point in time. Your program needs to be able to handle them all. So Boolean operators allow us to do this. Sometimes our simple expressions, they're just not expressive enough. So we've got to expand them. Let's take a simple example. Let's say you have 2 points on a plane, and you want to find out whether those points are in the same place or in different places. And so if their x coordinates are equal and their y coordinates are equal, they're in the same place, right? Or if their x coordinates are equal and their y coordinates are not equal, well, they're lined up one above the other. Or if their y coordinates are equal but their x coordinate is off, they're lined up horizontally, aren't they? But if I want to find out if they're in the exact same place, their x and y coordinate would be the same. So if I know the xy coordinates of these 2 points in a plane, and the first one has xy coordinates of x1, y1, and the other one has x2, y2, then I can do a comparison using an if statement, and I can say if x1 is equivalent to x2, I know their x coordinates are the same. Sorry about that. And inside that if statement, I could say if y1 is equivalent to y2. Well, if the first one's true and the second one's true, then their points are the same. If the second one is false, their points are not the same. Or if the first one was false right off, the points are not in the same place in this single plane. So it's still kind of an awkward way to do the evaluation because I have 3 possible outcomes, don't I? Here, only when both x1 and x2 are equivalent and y1 and y2 are equivalent do I say the points are the same. If either of those is false, points are different. So I have some extra code going on there. But what if I use some of those Boolean operators like and, or not? These allow me to compare 2 Boolean comparisons, and they both must be true, or maybe only one needs to be true. And we can do it that way. So for example, I can combine these 2 things together. This Boolean expression, x1 equivalent to x2, and this Boolean expression, y1 equivalent to y2. When I combine them together, or sometimes I could use an or, only one has to be true, this allows me to make a decision based on more than one possible comparison. When I use and, both sides of the and must be true. So for example, if I have variable p and variable q, if variable p is true and variable q is true, then p and q would be true. But any other combination would end up being false when putting p and q. Either they're both false or either one of them is false. They both must be true. In this truth table, and this is called a truth table, in this truth table, p and q represents maybe smaller Boolean expressions, like maybe p is x is greater than 1, and q is y equals 0, something like that. Since each expression has 2 possible values of true or false, there's 4 possible combinations. And if you take a look at the table, there are indeed 4 possible combinations. The last column gives us the value of the P and Q together, P and Q. This and operator saying that both the P and the Q must both be true. And you could write them out as true and true, and you would be able to get the same kind of comparison just to check them. So an OR comparison says if either expression is true. So if P is true and Q is true, then P or Q would be true. And in fact, what Python does when you have an OR, it looks at the first one. If it's true, it doesn't even bother looking at the second one at all. So P or Q would be true. If either one of them is true, doesn't matter which, I get a result of true when I put an OR between them. But if neither of them are true, I get a false. This table is the exact inverse, by the way, of this table. True, false, false, false. True, 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 false. So we can see that this is totally different. It's a totally different reflection of the two. The only time OR is false is when both expressions are false, and OR is true even when both expressions are true. It's not normally how we use OR in our natural language. If I say either this or that, you usually mean one or the other. And there is an operator called XOR that does that. But in this case, that's how it works. Now, the not operator just flips a value. Think of it like multiplying a number times -1. It just flips it to the opposite side. So if P is true, then not P is false. If P is false, then not P is true. It only operates on a single expression. So unless you put parentheses around multiple things, the not is only going to work on the value that's right next to it. Okay. All right, so we can put them together to make very, very complex Boolean expressions, and the interpretation of them relies on rules of precedence, much like algebra. So in algebra, you have exponentiation, then the parentheses, then multiplication and division, then addition and subtraction, right? That's your order of operations in algebra. Well, there's order of operations in Boolean expressions as well. For example, what if I have A or not B and C? Well, depending on how you look at this could be pretty complicated. Is it B and C first and then flip that with not and then that or A? Or is it left to right? Should something here happen first? As it turns out, the order of precedence from high to low is not and or. So in other words, not B gets flipped first. Then this one and C gets compared. Then the or. A or whatever this came out to be. That's how this works. And since most people don't really memorize that order of operations, what you want to do in your programs is put parentheses around those comparisons that you want to happen first. For example, if you wanted not the result of B and C, put parentheses around B and C. If you wanted the result of A or not B, then put parentheses around that, so that you know exactly what you're doing first. And that's how I strongly encourage you to do that. Let's go back and talk about our collocation of 2 points. If we're going to use and, we could say if x1 equals x2 and y1 equals y2. That whole expression could work out to be either true or false. And if it's true, then the two data points are in the exact same place. And I know what to do with my program if they are. Otherwise, they're not in the same place. They're in different places, and my program could do something completely different. So that whole expression, x1 is equivalent to x2, and y1 is equivalent to y2. The whole thing is only going to be true when the two sides are both true. So the ability to put together these expressions is very, very important. You're going to find that Boolean algebra, these Boolean equations, help you write pretty complicated programs that can do some pretty amazing things. And so we're going to practice quite a bit with them. But we can also do some algebraic equations. For example, a times 0. Anything times 0 is what? 0, right? Well, the AND operator can function very much like a multiplier, a and false. Well, it's false, right? Doesn't matter what a is. If I put it with and in the word false, I've multiplied times effectively 0. And I get the equivalent, the Boolean equivalent of 0 is false. A times 1. Well, that equals A, doesn't it? A and true. I get true. A plus 0. I get A. A or false. I get A, in fact. So the or operator is a lot like the plus operator. And we could set up very, very complex equations that can be expressed Boolean algebra and come out to true, false, or sometimes even a value like this one. A or false is A. So that works out pretty well. The or operator equates to A, if I say A or B, equates to A if A is true and equates to B if A is false. That's how that works. When A is true, it doesn't matter what B is because true or whatever is always true. If A is false, then the or operator is going to be false. And so you're going to get false totally, even if B is true. And you can take a look at some examples here. So for example, if A equals 1, B equals 0, and C equals the character A or B, 1 or 0, it's going to be A. It's going to be 1, right? It's going to be true because this is true and zeros and empty strings and null values are always false. B or A, same concept. A or C, same concept. C or B. C, this is not null or empty, it's true, or B. I'm going to get a true. The AND operator works in a similar way, except of course AND doesn't care as long as one side and the other are both true. And I just need to make sure that they're both true. But if A is false, then false and we don't care what's on the other side is always false, right? Because they both must be true. So if we start with false, then the and means that the whole thing is false to start with. So if A is true and the and operator results in B, and if B is true, the expression evaluates to true. If B is false, I get false. So we get this as a result. All right, anything or true is true. A or true, always going to be true. Both A and or can be distributed, much like algebraic equations. So A or B and C would be the same as A or B and A or C. A and B or C is the same as A and B or A and C. Double negatives will cancel out. So not A is just A. And De Morgan's law says that not A or B is the same as not A and not B. Notice this was an or. Now it's an and. And the reverse works as well. Not A and B is not A or not B. So you can distribute them out that way as well. It's actually not critical that you always remember this, but the general concept of how these work is very, very important. I take special note of De Morgan's law here. That's a good one to remember. All right, so as we practice with some of these, let's take a look at them. Remember, or returns true when both operators are true, and Boolean operators obey the rules of Boolean algebra. So for the following, A is 1, B is 0, and C is the letter A, what is the result of these equations? A and B or C is equivalent to A and B or A and C. How does that work? Well, are they equivalent? Think that one through. How about this one? Not A or B is equivalent to not A or not B. Are those equivalent? How about not A and B and B and C is equivalent to false or false? You got to think through these comparisons, see what happens first and next. Here's how the first three work out. A and B or C is equivalent to A and B or A and C. This actually comes out to the letter A. Here's how that works. Remember, C is the letter A. B or C. B was 0 or false. So B or C is going to be C. A, which is 1, and C is true. Equivalent to, and then you got all these that come around. What you end up with in the end is the letter A, and this kind of breaks it down of how you get there from one step to the next. You end up in the end with just C And remember, stored in C is just the letter A. It's not a true or a false. It's not a 1 or a 0. It's the letter A. Not A or B, equivalent to not A or not B. That is actually true, and it sounds familiar somewhere. Not A or B, equivalent to not A or not B. I think that was right here, right? Not A and not B. But the B had parentheses around it here. Does that matter? In this case, it doesn't matter. This is a true thing because this can be distributed to this. Not A and B, and B and C, equivalent to false or false. As it turns out, when we look at these and express them out, you end up with true, that this side, false or false, is false, and this side turns out to be false as well. So false here, equivalent to false. That's true. And this shows you how that comes out. All right, that's it for this lecture. Go ahead and take the quiz and move on with the topics for the rest of the unit. Get started on your homework and your programming exercise after you finish all the lecture quizzes, and have a great week. Take care.